40-meter center-fed dipole, and for my modeling, I'll just put it 40 feet above ground because that's a fairly common height. We have a 67-foot antenna, transmission line, and yes, there should be some kind of a decoupling mechanism here to keep the current off the outside of the shield. But that's about it. Pretty simple. What does it do? Well, this is its elevation pattern. The antenna is coming this way. And as you see, it has some radiation at relatively low angles. With the height, it has a fairly high peak load. Has a bidirectional pattern, as we're all familiar with. And if we look at the resonance characteristics, this is at its impedance that it wants to see at the particular height is 88 ohms. It very nicely can cover the whole band. Very handy arrangement. Let's take another antenna, a 20-meter dipole at 40 feet. Now, because the 20-meter dipole at 40 feet is twice as high electrically in terms of wavelengths, the pattern is lower. It's more low-angle radiation, fairly sharp pattern. The azimuth pattern is sharper, the nulls are deeper, and that happens as the antenna gets higher or the frequency gets higher. But similarly, we have now at 50 ohms, we have a very nice standing wave ratio of 1.5 to 1 across the band. Couldn't ask for better than that. So, great antenna. It's, again, not a multi-band antenna, a single-band antenna. What about using this as an antenna? They're have a lot of pluses. They're predictable, easy to make, good performance, low cost. The minuses are when you talk about multiple bands. If you want to cover all of these bands with single-band dipoles, you need an awful lot of trees and a big yard, and all of a sudden it's not cheap anymore by the time you're done with it. That's a lot of coax runs and lightning arresters and everything else that you have at work. So that's why there's such a push to have multi-band antennas. So one way we can do that, and this is very popular, is parallel dipoles. We just take the two dipoles and hook them both onto the same transmission line. And this works very nicely if you can make them not coupled together, which means you have them at a 90-degree angle to each other. And not everybody does this, but this is the best way to do it. And it can work very well. One problem, of course, is they share the same transmission line, so there's only one transmission line. It'll have one characteristic impedance. You can't have a different matching arrangement for each band, which you could with a single band antenna. As a consequence, the lower 40-meter antenna has a somewhat higher standing wave ratio. The 20-meter antenna looks about like it did by itself. Not bad. Now, what happens, though, is people try to make them supported by the same trees at each end and put the antennas quite close together. And people have been known to do it with zip cord, essentially in the same place. Well, the problem with that is this coupling gets in your way. It's not impossible, but notice what happens. The lower frequency antenna looks about the same way it did, so that's fine. What happens with the higher frequency antenna is once you can finally tune it to the right part of the band, which is not trivial because the antennas are so coupled together, the bandwidth is about half as wide. It's now 150 kilohertz instead of 350 kilohertz. And that's a classic problem with tightly coupled parallel antennas. Now, try to imagine doing this on 5, 6, 7, 8 bands with wires all coupled together, and you're out there with your diagonal cutters, and before you know it, you're down to a 2-meter antenna and have to start over. So this is possible, and it can work, but it's not as easy as some people would have you believe. So, parallel dipoles. Reasonable performance at low cost. If they're perpendicular, they work very well. But it's hard to get more than 3 mutually perpendicular antennas, right? In real 3-dimensional space. Now, they don't have to be quite that, but if they're not tightly coupled, it works better. One very handy antenna that works well is two antennas on two bands used as inverted V's holding up a pole. Perpendicular, they serve as the guy wires, works very nicely. Again, that gets you the two bands. Closed space dipoles interact, and are not an easy solution. They can work, but it's a lot of fuss. Oh. Okay. This is a folded skeleton sleeve two-band dipole, also known as coupled resonator dipole. That I had a lot of fun developing this, largely for a book Steve Ford was writing. He wanted a short two-band portable antenna. I spent a lot of time inventing things that didn't work. And I finally settled on this, which did work. It worked very well. So what it is it's a 40-meter dipole with the ends bent around, like that, fed by a transmission line. A 20-meter dipole is not connected to anything, and is separated by the distance of the window line, less than 3/4 of an inch. And it worked remarkably well, easy to duplicate, and it actually has a little bit of gain on 20. The first contact I made on 20 meters of this was to Australia. And interestingly enough, Bob Allison in the ARL lab made one and took it home and tried it. And the first contact he made on 20 meters was Australia. I did mine on CWD because it's on sideband. So definitely gets out. It doesn't beat a 3L and Yagi, but it does have a little bit of gain. And this is what it's, the solid line is that you have modeled standing wave ratio on 40 and 20. The X's are measured in the model I built for the article. So that's a very good two-band antenna. I had a subsequent article, and this was in May of 2011, if you want to look it up, I think. In October of 2011, I described arrangements for other combinations of bands. And every 3 months now, it's even, I don't know how many years ago that was, I'm getting requests. What about 160 and 2 meters? What about, all these combinations? So I've got a lot more, and if anybody wants more that are in the October issue, send me a note, and I'll be happy to send you the latest list of designs for this antenna. It just works amazingly well. There's also a ground plane version that I published a little later. So, consider that one. Parallel traps are another possibility. A parallel resonant trap acts like an insulator on the band it's resonant for. So for example, if this is a 40-meter dipole, about halfway along we have a trap resonant at 20 meters that acts like an insulator on 20 meters. So this inner part works on 20 meters. The whole antenna works on 40 meters. And on 40 meters, this trap looks a little bit like a loading coil, so it actually shortens the antenna a little bit. This is a very popular arrangement. It's the basis of most, but not all, tri-band Yagis and so forth. People are very familiar with. But it's also possible to use them for wire antennas as well. So that's been around for a long time. Here's the SWR between 7 and 10 meters. I extended it out further because what happens is because of the action of the trap, which has a different impedance on every band, not only at 40 and 20 meters, but every place else, it ends up making the antenna look a little longer or shorter on different bands. You often end up with a extra resonance someplace. So here's 40 meters, as you'd expect, the full length, 20 meters out to the traps, and then, oops, up here at 10 meters, it also has a resonance. It's not 1-to-1 SWR, but it has a resonance there. And this has been taken advantage of by some people. I should mention that, as you can imagine, to have a resonant circuit for 20 meters, there's an infinite number of L's and C's you can have that'll serve that function on 20 meters. And depending on how you pick the L and C, you can move this other resonance around. And that's what some people have done to actually get an extra band out of it. W3DZZ is the maybe first person to do that, or first person to publish about that in the 50s. And here's the response of a trap antenna. And I just point out, people say the problem with trap antennas is they're lossy. And of course, there's no such thing as a free lunch, but the loss is not that bad. Using the sort of nominal Qs that you have for the loss in the trap, the intensity on 40 meters of this trap antenna is 5.47 dB versus a full-length non-trap antenna of 5.87. So it's less than half a dB that you lose to get another band, and that's not too bad. On 20 meters, about the same. So it's, in my opinion, not a bad trade-off. Sometimes you need that half a dB, but most days you don't notice it. You probably lost it someplace else anyway. And here's the SWR of my model and trap dipole on the two bands. Again, looks about like the antennas by themselves. Let me, sorry I don't have a pluses and minus slide or skipped over it.
Question on the last slide, Bill. It's more of a EasyNet question. On the alternate impedance, were you looking at the 75 ohms and the 50 ohm rate?
I was just talking about the standing wave ratio on the coax itself.
Okay.
The assumption being down at the bottom, you could do something that's a good question. And has some ramifications. But in terms of the reason I did that was, in terms of how the antenna works, I didn't think it was fair to indicate a problem with the antenna because it happens to have a different characteristic impedance. There are a number of ways of dealing with that, but it wasn't really reflecting what the antenna is doing. Disadvantages of the trap antenna, the only ones I can think of are, first of all, they're heavier, so you have some weight pulling down. It tends to put more stress on the feed point on the ends. You also have a place for spiders to make home and so forth, and after a while, when they get tired of being overheated all the time, they die and make a kind of semiconductive mess. All of those can be dealt with in various ways, but otherwise it's not a bad arrangement. 40-meter dipole on 15. Everybody says, oh, third harmonic, it'll work fine. Well, yes and no. This is our 40-meter dipole. Tuned for the middle of the band. Well, what's the frequency in the middle of the band? 7.15. What's 3 times that? 21.45. That's off at the top of this band. A, and B, the antenna actually has a change in resonance. It doesn't have as many end effects. Each half-wave dipole has an effect of having the open ends, but you don't get 3 times of that because you only have 2 ends on the 40-meter dipole on 15. But in any event, the resonance on 15 is off above the top of the band, and we have a 10-to-1 SWR at the low end of the band. Well, if you have a long coax run, you're going to lose most of your power before you get there, and your antenna tuner may not even bring it in. So what do you do about that? Well, it's not all lost. You can do some other things. You can, this is now the 15-meter SWR. You can tune the dipole to be resonant on 15 and take what you get on 40. Now notice one thing, that the impedance of a 3/2 wave dipole is not 70 ohms, as a half-wave dipole is in free space. It's more like 125. And in this case, with probably 40 feet off the ground, it's about 110 ohms. So you've got a 2-to-1 SWR at least to deal with before you do anything else, even if it's right in the middle of the band. So that's a little bit of an issue. But it's a lot better off because now the standing wave ratio on 40 is not perfect, but it's better than it was the other way around. And the loss on 40 meters in mismatched coax is less than on higher frequency band. So you're better off, if you're going to do it, you're better off tuning it for 15 and taking what you get on 40. For some reason, I spent more time fooling around with this than I probably should have. So you can also feed it with 75 ohm coax instead of 50 ohm coax, which gives you a better, closer to the impedance of the 15 meter antenna, and actually gives you a better SWR on 40 as well. Now again, you have to deal with that down at the radio. Most radios can deal with it. They have an internal tuner or something. But, so that's another possibility. And yet an additional possibility, especially if you like 15 meter phones, to tune it for the high end of 15 meters, which brings it in at the low end of 40 meters. So you can fool around with this, and the point is a 40 meter dipole does not automatically give you good 15 meter operation, but if you do a little fussing with it, you can actually end up with a reasonable compromise that will work for you depending on what kind of operation you want to do. Does that make sense? I mentioned at the bottom, I forgot to point out, there are other things you might think of. Well, what about 80 meter dipole on 30 is almost a 3-to-1. That doesn't work as well. What about a 30 meter dipole on 10 meters, which is almost a 3-to-1? That doesn't work as well either. It's like 20-to-1 is WR or something. So 40 and 15, you know, I thought about it last night, middle of the night, for some reason. What about 160 and 60? That's actually a possibility, but I haven't done that yet. But it's possible.
Yeah, do that tonight.
I'll do that tonight when I sleep. Anyway, interesting pattern, and this is a plus or minus. You know, we looked at the pattern of a 40 meter dipole perpendicular to the axis of the wire, pretty much bidirectional. On 15 meters, we get this nice 6-lobe pattern, very different. The 40 meter dipole would predominantly work in this direction on 40, but on 15 we get lobes in slightly different directions. Now that can be handy. If you have an antenna you can't turn, and you want to work somebody on some island someplace that's going to go their azimuth, if the antenna has a pattern that's favorable in that direction on another band, you wait till the expedition is on that band, and you go find it. I've made good use of that over the years. Because most of my antennas were antennas that couldn't move except with the rotation of the Earth, which the DX station moves at the same time. Anyway, so sometimes you can make good use of multiple different patterns. Now this is one that everybody loves, I guess. G5RV. 102-foot center-fed dipole, not resonant very much anywhere, although I guess it's about 30 meters. When I can't think of his name. Anyway, when G5RV invented this, there was no 30-meter band. The bands were 80, 40, 20, and 10 were the HF bands. It was right after World War II. He did not set out to make a multi-band antenna. He wanted to have an antenna that had a narrow beam towards his buddy in South Africa from England. And so this is a nice length for that. It has a fairly sharp peak off the perpendicular to the antenna on 20. He found that if he used some, in this case, 300 ohm twin lead, and then transitioned to 70 ohm twin lead, it actually did the matching for him, and he could hook that to the link coupling in his transmitter. Well, people didn't worry about standing wave ratio back then. They didn't have a way to measure it very well, and it worked. And he had good luck with that. And they found out that actually you could make it work on 80, 40, and 10 meters as well as on 20. And his suggestion was, well, if the impedance is not right, just use your halyards and raise and lower the antenna to tune the impedance to what you want. I mean, these are all great solutions for him, but probably not for us. Now, what I found is if you take a G5 RV and you model it, you do indeed get a bunch of different resonances, as you can see across the HF spectrum. But this particular set of dimensions that I used, you get a 3.6 to 1 SWR on 75, 2.2 on 40, 70 to 1 on 30 meters. Well, there was no 30 meters, you didn't know about that one. 2 to 1 on 20, not bad. 15 to 1 on 17 meters. 28 to 1 on 15 meters. And so forth. So you do get multiple resonances, but I've never been able to make them all line up in the same place. Now, some people say, well, the answer to this is use 100 feet of RG58 coax from the matching section to your transmitter, and that will help match it for you. Well, yes, it does, because the loss in the transmission line makes it look very good to the radio, but most of your power is heating up the coax, not radiating, but some of it is. The other problem is, if you want to go adjust it, you've only got two things you can adjust: the length of the antenna and the length of the matching section. And you want to make it work on 8 bands. Well, there's no way you can make everything come out even. And plus, what always made me crazy, it's never obvious to me which direction you want to go. You want to make the antenna longer or shorter to move it on 80 meters, because part of it's happening in the matching section, part of it's happening in the antenna, and unless you're modeling it or doing something, very difficult to tune this thing. But it will work reasonably well. How many people use G5 RVs? Yeah, I've used them.
Lewis Martin.
Pardon me?
Lewis Martin.
Thank you very much. Yeah, Lewis Martin, the commander in the Royal Navy during the war, and published a number of other articles as well. Anyway, it's a useful antenna, but it's not a panacea. It is not quite as good as people who sell them would like to make you think they are. And even within a band, it's not necessarily that the rhythm will cross the band. And you can make some adjustments here. You can, if you're focusing on 80 and 40, you can probably make it come out right. But again, you're going to waste a lot of wire before you get it right. You don't know which way to go with anything. Question?
Do you have any experience working with cutting a G5 RV or working with CW lower end of the band?
I've tried.
Yes.
Yeah. You can always make it work on one band, but of course that's pretty easy to do with a dipole. And by the time you get it right there, it's completely wrong every place else. I mean, that's just my experience. And here's some other, it does, okay, so it has a resonance of 2.5 to 1 resonance on 15 meters. No, it's not, actually, it's near 15 meters. This is 19, this is 22. On 15 meters, it's 25 to 1. So, what do you do? Shorten it to make this come out here. What does that do to everything else? It's really tough to do. It has an interesting pattern. So briefly there. Interesting pattern, different on every band. I had actually had azimuth plots when I used mine, other on each band, overlaid in different colors, so I could see exactly what band I wanted to switch to when I was going after a DX station. And if they were in the nulls, I didn't even bother. If I could hear them, they'd never hear me. So it's pluses, it's low cost and simple. It works well on some bands, and it's fairly short. 100 feet is a lot easier than 140 feet for a lot of people. And if you have another antenna for the higher bands, it'll work on the higher bands when that antenna falls down, so it's a good backup. So it's not, it's not a zero, but it's not, my point is, it's not really the one antenna for everything. So that's my opinion. And there's some other ones, similar kinds of things. The G0 FAH, slightly shorter, slightly longer matching section. Never took off for some reason. Doesn't work on 80, but works on the other bands slightly better. this is a very nice one. This was just published in QEX for March of last year. A antenna for the WARC band, so-called WARC bands, which people say I shouldn't use that word because those are the new bands to me, but that they came out in what, 1978 or something. So for most people, they've been around longer than they have. But this works on 30, 17, and 12 meters. A lot of antennas work on the traditional 80, 40, 20, 15, and 10. This one works very nicely on the three relatively new bands. Same idea. 37 feet. I guess this is Zach. This is Zach Lau from the ARL lab. Did this. He used 600 ohm open wire. Where I modeled it, I found that with if you use window line, which is a little easier to deal with, you use the same matching section and you just shorten the antenna a little bit, and it'll work the same way with window line. So look at this SWR. $30, right on. 17, very close, and 12 meters, right on. Now, he had another version of this that was in this month's QST. Did everybody see it? For 40, 20, and 10 meters. Unfortunately, that one doesn't hit the bands quite as well. He kind of says, but not quite loud enough. You really need an antenna tuner to use it on the lower band on the 40, 20, 10 version. But there it is. You know, same idea. So a 3-band antenna. So it's sort of like a G5RB in principle, but it's just a different size for different bands. So that's another possibility. This has a dipole pattern on 30 and 17 and kind of a multiple lobe pattern on 12. Now this is the W3 DCZ multiband dipole from the 50s. It's an 80-meter dipole with 40-meter traps. So that gives you 80 and 40. But with this fortuitous resonance thing, it has resonances on some of the other bands also. And this is actually made commercially by the Unadilla trap people who offer this as a kit. I've used it. It kind of works. Well, I mean, nothing. So here's what the model shows. It has a good SWR on 80 and 40, as you'd expect. Not good on 30 meters, which wasn't a band when it came out. 3.6 to 1 on 20, not bad. Not so good on 15, and not so good on the higher band. So it's good 80, 40, and 20, but with just 2 traps instead of 4 traps. So. Now it's easier to adjust in the G5RB because you can adjust, you know where the 80-meter part is, it's the outer end, and the 40-meter part is the inner side. You can't adjust all of that and have 20 come out exactly right at the same time, but there's, at least you can go to the separate adjustments for 80 and 40. And it can be a backup antenna for the other bands. It's not a bad, when you're going to have an 80 and 40-meter trap dipole, you might as well have one that gives you some hope of working on other bands too. Now this is one that I've been using for a while, and I've been quite happy with most of the time. Non-resonant tuned feeder dipole. We're doing fine on time. I'm talking fast. Anybody feel like I'm talking fast besides me? No.
You're doing great.
This works best if it's a half wavelength on the lowest band. It doesn't quite have to be. For example, I've used the G5RB length, 102 feet, on 80 meters very successfully this way. Virtually any length of window line, balanced antenna tuner. No losses in traps, low loss window line or open wire line. Works very well on all the bands, as long as the impedance at this point is something the tuner can handle. That's the one that will catch you. People say, and I used to say, any length of window line will work, Well, maybe not. But what I say to people now is, well, leave yourself a little extra and trim it a little bit if it doesn't work. 6 inches at a time, and it will work well. I went through this. I recently moved my shack. I get upstairs and downstairs shack now, and had to have a separate run from the entrance panel. And I can plug in the antenna line going to my office shack up first floor or my basement shack, depending on which one I'm using. And I had a heck of a time getting it to work in the new location. And finally what I did was I took, I don't know if people are aware that it used to be the test equipment used double banana hooks, 3/4 inch spacing. People know about those? Very handy. What's nice about them is it's about the same length, the same spacing as 450 ohm window line. So they're a natural connector for window line, and they plug in and out very quickly. So what I did is I made up sections of window line of 2 feet and 4 feet and 8 feet, 16 feet, and then I could make increments, 2-foot increments of anything from 2 to 30 feet of window line. And so what I did in the basement where the transition to coax was, I just kept trying different lengths and find, oh, this works on this band, but it doesn't work on that band. Anyway, but sooner or later you find a length that will work on all bands, then you take a piece of window line that long and put it in and save the little short stubs for your next experiment that you think will work with any length but won't. So it's important that you have an impedance that your tuner, and this is as much a tuner question as an antenna question. But typically, the very low impedance loads are a problem for tuners, as are the very high impedance. This is not surprising. 60 to 1 SWR, the tuner's not going to work. And you can easily get that. But you can find a different impedance, because impedance is variable along the length of the line that's not matched. So you can just find a different length until you find something that works. So that's a very good, people call this a center-fed ZEP, and some people argue about that, but it's pretty descriptive, I guess. The ZEP, the traditional ZEP is just one wire and balanced transmission line matching section that was used as a trailing wire antenna from Zeppelin airships is how it got its name. So center-fed ZEP is doesn't quite fit with the Zeppelin airship, but it's sort of descriptive. Anyway, it's a very good antenna in my opinion. Has various, again, each this is the length I have, 132 foot. It has a different pattern in every band, and it really helps to know what that pattern is, because if you talk to somebody over here, they're not going to hear you, and you probably won't hear them. So you don't even know you're missing it. But when they show up on another band, you will work on that. So there's not much not to like about that. A couple of other bands here. This is 20 and 10. Oh, this is a 102 foot version of 20 and 10. And here's an 86 foot version. This is very popular because this on 20 meters is the maximum gain you can get from a single element antenna with a single lobe. Notice the very narrow beam you have on 20. So it's great if you want to talk to somebody perpendicular to the axis of the antenna. It doesn't work so well in most other places. But it does. It's like a 5/8 vertical, a pair of 5/8 verticals end to end. So 86 feet is not surprisingly like a 43 foot vertical, except turned on its side. Again, it helps to keep track of this if you want to work with people in particular directions. So the pluses of this kind of thing is it's very efficient and low loss. Has complex pattern on the higher bands, which is because each of those lobes has a lot of gain typically. it does require a wide range tuner. So you, instead of having an expensive antenna, you have an expensive tuner. Often they break about even.
Joe, how do you get the ladder line to the tuner into the house?
Good question. I just bring it in through the. I have an entrance panel that has coax lightning arresters right at ground level, ground system right there, coax lightning arresters, and I have a balance line lightning arrestor for the window line.
So you bring it just like a coax?
Yeah, and you have to be careful where you put it because if it goes next to lossy things, the problem with window line, or a problem with window line, is that with coax, start with the other thing. The nice thing about coax is it's working properly. All the fields are within the coax, not outside the coax. So you can run it through pipe, you can run it next to wiring, you can run it next to plumbing, you can coil it up, you can do all that kind of stuff. You can't do that with window line because it'll foul up its operation. Fields in window line extend about 2 to 3 times the spacing outside. So there's a imaginary tube about this size going along with your window line, and you have to keep it away from lossy things. If it goes near metallic things, it's not quite so bad, but it changes the impedance. Of course, in most cases, you don't care too much about that. It doesn't generate loss. But if you coil it up, it's all bets are off. So one thing I've done is I've gone through a wall with a pair of RG213 cables about that long, the shields tied together at both ends to make a shielded, balanced line. Doesn't match the impedance, but I went through 8 inches of footing. This is from my rhombic at one point. And I had window line on each side of it in the clear, but going through the wood footings, I guess I'm sitting on the foundation. That worked fine, so that's one way to do it. The other thing you do is put the coax to window line transition on the outside of the house. You need a very short length of coax because there will be high loss. There's high loss in the balanced coax also that I did, but I only had a piece about that long going through the construction. So there are a number of ways to do it, but it does have a complication. Another thing to do, there are a lot of automatic remote tuners. So we put the remote tuner outside, if it's weatherproof, and bring coax in, and that avoids the mismatch problem on the inside. So anyway, that's a nice antenna. And the other nice thing about these, while I'm trying to make the slide come up, is the adjustments are made at the bottom. If you're trying to tune some other antenna, you're tuning it at the top. Well, you could have to be really good at climbing trees and towers or lowering and raising antennas all the time, and after a while they have to figure out. So this, you do everything. You put the antenna up and you fuss with it downstairs rather than outside, which this time of year is particularly convenient in my experience. Okay. Wideband antennas. I'm not going to talk a lot about these because a lot of people don't use them, but it's worth mentioning them anyway. There's a kind of antenna called traveling wave antennas, which are antennas that, rather than an antenna inherently, most of the antennas we're talking about are standing wave antennas. They have a current pattern on them that has a minimum at the ends and a maximum at the often at the beginning. Okay? I think we're on track. But the traveling wave antenna is like a open wire transmission line pulled apart. As you know, if a window line or open wire line has the conductors too far apart, the transmission line will radiate. Now, in a transmission line, you don't want that to happen, but if you pull them out apart far enough so it radiates well, all of a sudden, instead of a transmission line, you've got an antenna. That's what a rhombic is. It's a balanced transmission line with a dummy load at the end and very far apart conductors so that the fields line up in such a way that you get a pencil beam off the end, and it covers at least a 4-to-1 frequency range with good results. And I wrote an article about the imperfect rhombic, because you don't have to, you have all these tables and charts you go through to make an ideal rhombic that's going to work the way it's supposed to. Well, unless you think ahead and plant your trees 60 years before to hold this thing up, you're not going to do it. Well, I made a rhombic around and connected two trees on both sides of my house and fed it from both ends. Worked reasonably well until one of the trees fell down and took it down. But you can make a rhombic work. A V-beam is half a rhombic, and it can be terminated also. And it, again, 4-to-1 frequency range, pencil beam, it works very well. A half rhombic is one you don't see much about, but it's a very useful antenna. It had a single high support structure, and it basically goes from ground level up to there and down to the other side where it has a termination. It's a vertically polarized antenna, has about a 4-to-1 frequency range coverage at least. And I had a doctor column, somebody built one and used it from some island on a trip over to Scotland or something, and raved about how well it worked. It has to be fairly high in the middle. But those are all traveling wave antennas. They have useful gain, but they're larger than, say, a Yagi with the same gain. So, but they're made out of wires, so they're cheap. Yeah, let me finish up, and then we can talk. The other category is log periodic dipole array, which is a collection of dipoles of tapered size, and the signal is fed down the array, and it sort of ignores the dipoles that are not in the same right frequency range, and it uses the 3 or 4 in the proper frequency range as kind of a sort of a Yagi, a driven array. And it provides gain similar to a small Yagi. The problem with it is, and typically 4-to-1 frequency range, and they can work very well. The problem is on the high frequency range, they're only using the very small part at the end, so you're kind of throwing away most of the antenna. So if your focus is on the low frequency bands, and the high frequency are kind of a free part for a little bit extra, it's not bad. But if you're focused on the higher frequency range, you're really wasting most of the space. You could do a lot better with something that is a tuned Yagi that operates efficiently over all of the frequency range. But they're very popular for people that need to cover a very wide range. Another one that sort of in a category by itself comes up is a tilted terminated folded dipole. Anybody hear about that? This is the one that's a combination antenna and dummy load. And again, it's gotten a lot of press from different people, and some people can't imagine why anybody would do it. There's some reasons for it. For most people, it doesn't make any sense. I did write an article about it, so look it up in QSD. And a disc cone is kind of a vertical antenna that's, for HF, it's usually not very efficient. It takes an awful lot of metal, and, but sometimes it's useful with VHF. So I think that's most of what I had to say here. So we talked about all of these antennas, and kind of wrap up. And I should mention that all that we talked about in terms of dipole and horizontal dipole antennas pretty much, but they all apply to vertical antennas. You just turn them on their side, feed it against the ground, and it's half as big, and everything else is about the same. And arrays of multiple elements. All of these antenna designs can apply to fed arrays or other kinds of arrays just as well. So the same principles work for all of them. And a word from your sponsor. We've got there's a couple new books since the last time I was here, but and I haven't been asked to write any more lately. So I guess people are less interested in books. So buy up books and keep them going.
Joe, could you comment on some of the end-fed antennas, like the ours, multiband end-fed, that seems, I've used very, very effectively at QRP. But I can't figure out how it works.
Well, end-fed antennas inherently don't work. Well, I mean, what I mean by that is that they really don't work. You can't feed, it's like one hand clapping. I mean, you have to have something on the other side, and it doesn't have to be much. But what happens is if you don't have something on the other side, the transmission line itself becomes the other side, which is something we call common mode current, which is something we try to avoid. So one thing you can do is you can choke it off in a couple places, but you have to have something there for the others to be the other side of the antenna. Otherwise, it just doesn't work. You can't model it, for example. An end-fed antenna can't be modeled by itself. The model says this doesn't work. So there are things happening that you aren't aware of as part of the antenna.
But they do work.
But they do work
I worked
because
Australia on 10 watts.
yeah, they do work because it's not what you think it is. It's not an end-fed antenna. It's an off-center fed antenna with the outside of the shield of the coax serving as the other part. So that's the caveat. And so does that mean it's not an antenna? No, it means it's not an end-fed antenna. It's a off-center fed antenna in effect. And that can work, no question about it. And why do they work on multiple bands? Well, if it works on 80 meters, it almost looks the same on 40, it almost looks the same on 20 in terms of impedance at the end. So if you can make the match work somehow on one band, it works on the others. But the trick in those is what you do on the other side of the antenna that you don't think of as the antenna, how you decouple that. Same off-center fed antennas have the same kind of issue as well. Now I think I need to get out of here now.
Wait a minute.
Pardon me?
You got one more question.
One more question, okay.
The half ohmic, you said, needs to be fairly high. How high is fairly high?
I don't remember. And of course, it can be as high as you want, but at the lower frequencies it won't work as well. So that's the other side. I mean, it's a non-resonant antenna. And what's interesting about it is the termination at the far end, which is about 400 ohms or something, has to be fed against ground. But it turns out, because the impedance is so high there, it doesn't have to be a good ground. It can be a minimal ground to work, which is kind of interesting compared to a lot of like quarter wave antennas fed against ground. And it has a lot of unidirectional gain, and again, cheap and simple. I found it in an old Army manual one time. But that's, you know,
Well, could you just comment on long wire antennas? You know, antennas that are like, 400, 500, 600 feet long.
yes, they're only good if you have a lot of property.
Right.
But actually, somebody, while I have to get out of here for the next day, but while I'm doing it, I'll talk because I pulled up the tent here. Somebody wrote me, I get a lot of questions